Okay, my friends, get ready, sit down, get a cup of coffee, tea, whatever you drink, and get ready for school, because it is not what you think it is. School is supposed to be a place of learning, of understanding. It is not. It is a place of indoctrination now. We're going to start all over again today. Okay, my friends, Roger once again. As you know, I was going to start a new school, and it is starting today, and it will be online, and I am going to start from physics top to bottom. And I was involved in this when it first started, 1970. I had the theory that there was nothing but dipoles. Dipole means a positive and a negative. You see this on this screen right here? This is a fixed particle, and that's a point particle. This is Fermilab. They can see these two particles. They don't know where they came from, because they're hitting head-on billions of particles at a time, and this is the smallest particles they see. We see them, and not only can we see them manifesting from light, not from proton smashing, so it's not garbage. My theory 50 years ago was there's only two types of power, which basically is dipole-to-dipole interactions. And also, this is the most important one, is the transfer of energy is from light to atomic vapor. And what is light? Light is no more than two of these particles back to back as a photon. I'll show you light right now. Okay, I'm going to be brief with this because we're going to get extremely deep, so there's no sense in getting deep right to start. This is the particles that Don Lincoln from Fermilab, and this is in 2013, the same time we were doing our research, they saw these particles, and here's what he says about those particles. Let's just go right to the summary. In summary, extended particles have a fixed size. The fixed size particle is the black one. And they have a fuzzy edge. Yes, it's a black, you see it? Whoops. Here we go. See the black and the fuzzy edge around it? And you see just a white glowy one? So the black one is the extended particle, have a fixed size. They may have a fuzzy edge, which they do. The point-like particles are mathematical abstractions with zero size. Now, I don't know if that's true or not, but I can't discount that. He says, even though they have a zero-size particles, have an extended effect due to the effect of the field surrounding them. Well, it's a field attached. Whoops, I do that every time. It's a field attached to that particle. It's not, if it's not a particle, if it's a field surrounding, if it's a surrounding, something has to be surrounding, there has to be something there. Although I have to agree, I cannot find any evidence that there's any mass to this part. This, yes, and I think this carries basically all the mass, but at least they claim at least 80%. That's dark matter and dark energy. And it gives off no light, and here's how we can show that we found those. Here they are right here. Remember the one Don Lincoln showed? And the glowy part. This is light. We didn't start with protons, which is just gigantic particles. And when they slam together, you just have nothing but a pile of trash. And in that trash, this is the smallest bits of trash they can find. Well, we found them too, but we found them in light, and we can see them manifest themselves as this particle, which is this particle here, which is these particles here. There's the black one with this little glowy edge. It's hard to miss that one. And here's the little glowy jobber down here. Now, what do they do when they actually concuss at what we created was a venturi right here? Rod Warren discovered this quite by accident, but when I saw it, I knew exactly what he had done. And he worked with me for years, and he still does, and he deserves an extreme amount of credit for this, because nobody would put up with me for years like that. Now, he accelerated that light. If you can't see an acceleration there, you got some problem with your eyeballs. What is a particle wave? A particle means you have a magnetic field, a magnetic particle, which is like two little bar magnets. Shown it a million times, and here they are right here. Two bar magnets, a positive and a negative, positive, negative, positive, negative. Basically, that's it. The black is exactly the opposite of the white, but the black is gravity and sucks the white to it extremely hard, and the blacks suck hard against each other. The blacks just want to be in a ball together, and we have seen them literally congeal into a ball in space in a Russian experiment in a vacuum tube in space, putting ionized particles in there, and it created just a big round dark matter circle. I'm 100% sure of that. Well, when I say 100%, I saw it with my own eyes. You'd have to look at it and think for yourself. But what I just showed you was the muon neutrino, the black ball, the electron neutrino, the white ball. All right, so let's make sure we see it again. The black and the white balls, and the reason this is light is because they're attached together. Half of this, just one black and one white, is what's called an electron. In this gauge theory, they would call this a gluon, and they would call this a W boson, and this a Z boson. And they would call the whole thing together, I can't even remember what they call that one now, but it's just a photon. We'll look at the gauge theory in a minute, but everything is explained to what is observed. That's the glowy particle, that's the muon particle, and here they are right here. The glowy one is the electron neutrino, the black one is the muon neutrino. They were attached, and then when they hit this new medium, which we did here by crushing it into their own fields, causing the Kashmir effect, which is head-on collision, is nothing more than crushing side by side. They're in a well right here. The black particle, the muon, can't get through that well. It just slams, 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 and pushes the white through here, sprayed out, and the white just does not want to be next to each other, so it just pushes like crazy. I think we can harvest energy here. I just did a video about it showing that from this original light, photons of light only take a couple of electron volts. Coming out of muon territory, which is nothing more than cosmic rays, creating muons, if we did it, and we did, you have trillions of electron volts. That's a pretty good increase. If we could harvest some of that, we should be able to have free energy. And all this stuff exists today. So this is where I'm starting from. I've been a long time doing this. So this is not my first day on the job. And everything that Fermilab said, I said. And I showed them everything that I said. And here's the other thing I said that they say too. Whoops, this is one of them here. This is about using this for cosmic ray detectors. This goes back to the same time frame. And that's all we used was a cell phone. And it was the same technology to use as is in high-end multi-million-dollar observatories. Same technology. It uses the same principles as these very large experiments. And cosmic rays are what? They create showers of secondary particles called muons. And that's what they're looking for, is the muons. And that's what I just showed you was the muons, right here. Muon neutrino, electron neutrino. This is what they want to see, was the black one. That's the one they could never find before, because it's dark matter. That's why they're so interested in a muon. And that's where all the weight appears to be. Now, I want to show you what Yale has to say about quantum physics, which this is as quantum as you can get into the quantum physics range. This is the separation, literally, and I'm not kidding you, this is fission here. You see the black is no longer attached to the white. That's called fission. When they come back together, they fuse back together and become the black and white pair that we saw originally. That's fusion. Fission, fusion, in between, God only knows. But if we can use it to get energy, and they say it's supposedly trillions of times more energetic than the particle sitting on its own self, attached to what they would call a gluon. All right, I'm going to say it one more time. These are the tiniest particles they could find. Here they are attached together as a photon, because that's what this is. This is from light, nothing other than light. We split them apart so we can see this can separate from the glowy part, which means this is that black sterile muon once we get it down into this range here. It's what's called a sterile muon. These are the electron showers. Now, let's see what Yale has to say. All right, like I said, I did a video on this the other day, but we're using visible light photons, maybe a little higher than visible light. Let's say we're using 10 times more power than it takes to make visible photons. So instead of 1.5 to 3.5 electron volts, let's say we're using 100 electron volts, 500 electron volts, 1,000 electron volts. Let's go with 1,000. If it took that to make the light that we just used to make that white spray, what was that white spray and the black particles? Well, guess what? They were cosmic ray energies, and they are in the trillions of volts. 1,000 trillion electron volts versus, what did I say, 1,000? Let's give it 100,000. Yeah, give it 100 million. It's the increase in energy is just phenomenal. Why can't we even try it? It's been so pushed back at, it's just unbelievable. If the separation of powers here, which is absolutely separated, no question, I showed it. If we can harvest it right here with, they have these thin film perovskites, and they got all kinds of new exotic materials that absorb, which might be just raw electrons. I don't know what this is at this point. This is what we need to have tested out. I can't do it. This was just an accident that we stumbled onto this. But this is my background. I understand it very well. And this exactly proves my theory. That's why I am so persistent here. My theory works, and it has worked since 19 bazillion years ago. Because that's all there is two little particles, the black and the white one. One of them's energetic and burny and glowy and seems to have no mass. And the other one carries it and is a big, heavy-duty bowling ball that never changes its size. It doesn't absorb any energy. It doesn't appear. It doesn't emit any energy. It just is an attractor of the white particles and of its own self. So it is gravity, and because it doesn't emit, absorb, reflect, and do all the things that dark matter doesn't do. It's dark matter because dark matter is gravity, and they've never seen it before, and now we see it. All right, I'm just not screaming in the woods just for no reason. I want to see us get free energy and create something that can help everyone's lives be better and save the Earth. Hopefully, I'm going to do as much as you can. It's kind of late in the game, but we can do what we can. Now, again, we saw that this is the particles of light. That's from a red pulse laser. It's got to be light. It can't be anything else. It is light. No question it's light. And at this point, it's this particle. Just as it hits the Venturi, it breaks into these two particles, which is the smallest particle CERN has ever seen either. So we're all on the same page. Why can't we use this as a collection device right behind there and suck off all that trillions of electron volts? Coming in light is, well, I show you the equations. They love equations. I like physical. I'm a material scientist. I see something. You could talk to me all day long about gauge bosons, this and that, having no mass. This is the first thing out of Don Lincoln's mouth. He came out, oh, everybody knows it doesn't have any mass. This doesn't have a mass. No, we don't know any of that stuff. Not a word of that stuff do we know. We have to start from the beginning. And that's why they won't even talk to me, because I won't agree that a gauge boson has no mass. All right, so here's the professor. He's walking in to greet the students. This is Yale. Like I said, back in 2011.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, And the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So, all right, so that's the spirit in which we are doing this. I want you to think about this as a real adventure. Try to think beyond the exams and grades and everything. It's one of the biggest discoveries in physics, in science, and it's marvelous how people even figured out this is what's going on. So I want to tell you, in some fashion, but not strictly historical fashion, but purely historical fashion is pedagogically not the best way because you go through all the wrong tracks and you get confused and a lot of battles going on, and when the dust settles down, a certain picture emerges. And that's the picture I want to give you. In a way, I will appeal to experiments that were perhaps not done in the sequence in which I described them. But we know that if you did them, this is what the answer would be, and everyone agrees. And they are the simplest experiments. All right, so today we're going to shoot down Newtonian mechanics and Maxwell's theory. So we're like the press. We build somebody up only to destroy them. Built up Newton, shot down. Built up Maxwell, going to get shot down. So again, I try to drill into all of you the notion that people get shot down because somebody else does a new experiment that probes an entirely new regime which had not been seen before. So it's not that people were dumb. It's that given the information they had, they built the best theory that they could. And if you give me more additional information, more refined measurements, something to the 10th decimal place, I may have to change what I do.
There's the issue right there, my friends. I have presented something way past the 10th decimal place, and evidence, when I say 10th decimal place, I'm just teasing. I have shown the evidence that I have shown to support the facts that I claim are the new physics, which is dipole flood theory. And here it is, right here somewhere, here we go. Extremely simple, replaces the things he said nobody can understand. This explains the Feynman diagrams elegantly, absolutely no question whatsoever. They think these particles popped out of nowhere land because they're using protons colliding. We're using electrons colliding and photons, so we can see how they manifest themselves. We're in a much more elegant realm than they are. We can see the photons. They're now calling these tetraquarks. They have to use their proton colliders. They spend literally trillions of dollars. And this is all over the world. This is not just Fermilab and CERN and Jefferson Lab and JPL and NASA, and I mean, there's a bazillion of them doing the same thing, and none of them are getting anywhere because they have to conform to this gauge theory, which says that a photon has no mass. It absolutely 100% has mass, and I can show you, and nobody can stand in front of me and argue with it. This is the key. It's not that if you get more evidence, change your mind. No. They suppress that evidence, and now we're going to have to do it ourselves. That's why I'm starting this new physics school. So if you want to learn real physics and you want to be of value to some future employer, stick around here and learn the trueness of the situation. You're going to hear exactly what they have to say. I always give it both sides. I'm not a one-sided guy. I listen to everything. But I have seen, and we can create all of the things that they're looking for, and they refuse to engage. Now that really worries me about education. It should worry you too. Okay, now, you saw the wave, that big wave. Now we're really focused in here into the particles that are within that wave. You see these little flat looking ones here? And then you see, if you go straight down the line, you're going to see this right over here. This is the Venturi. At this point is where they break apart into the black and white. But just before they do, they manifest themselves as what is known as a photon. Now, a photon consists of two bar magnets. And if you think of what a bar magnet is, it's a dark and a white, black and a white. So this is a bar magnet. This is a bar magnet. They will always have their orientation towards Earth, so they will always spin this way, and they actually tumble in a spin. You see how the black is in front on this one? And when you come over here, the white is in front. It had charged up and flipped. It's the same particle because we're catching them all at one shot. You get a whole row at once. Now, this particle at this point is showing a muon, an electron neutrino, a muon, electron neutrino, and they have a plus and a minus charge. I can go along with that because they're dipoles. And then when they hit here, they actually separate into their own separate particles. Now that's red. Green is the same particle because photons are photons, but one has energy in abundance and one does not. But you can see the blacks pull the whites together, but the whites want to push away from each other. They really don't like each other. Once they're on their own, they will not stay on their own. They'll grab a hold of, or a black will grab a hold of them one way or the other. And here's an electron. These are the green in flight, and very, very powerful. And remember I said they charge up as they go forward, but they have this polarity towards Earth. This one is just getting ready to flip. It's charging. You see how it's getting all fuzzy in the front? Normally they look like this. Well, no, when you see them in their perfectness, they're like this. That one's getting ready to flip. Now, let me give you the whole shooting match at once. You saw the green, you saw the red. Let me just see if I got blue laying around here somewhere. Here it is. Blue is much faster. You see it coming in fast out of the Venturi. When it comes down to where you can actually see the two particles. Here you would never know there's two particles. But the key here is you can have them go faster, you can have them go slower, you can speed them up, you can slow them down. Light is not a one-shot deal. All right, so let's get up to here. 21 is the one I want to show you. Here's the whole shooting match in one pile. The particle coming through the air, the particle accelerating out of the wave, creating its own little pathway here and exploding at the Venturi. Now the blacks keep hammering this well, because the Venturi is an angular device that makes all the fields coming at it, forces them to crush each other. A crushed field is what's called the Kashmir effect, which means head to head is the same as crushing them here. No difference whatsoever. But we're continuing to slam them with those black particles, which are these black particles. All right, I've shown them many times. They detach, but they can't get through. They can't get through. So the white ones get squirted out, and then they recombine. But in the middle, somewhere along the line here, they say that splitting them, creating these muons, should give us trillions of times more energy. You know, that's quite a bit. Now, this is the white particle sizzling right out here. There's nothing in between here. These ones way out here are right on the edge. All right? This is the center, and in the center here is nothing but these white sizzles. All right, I have better shots of this, but right in here, there's no Higgs fields. When they come way out here and hit, yes, they start back up again, and that's way out here, in the center. On the edges, they show right up. You see way back here, you can see them on the edges. As soon as the particle is able to hit a black particle, and I think there may be more black particles in the air than there is white ones. Because when you see it coming through the Venturi and reattaching, it's hard to believe that all these black ones could get out front quick enough from this impact. I think there's extra black ones here, but a lot of work to do. This was a really phenomenal event. This one here, I think, was a reverse spinning particle and hit a correct Higgs and spun that off, which I don't know what it is, but it's not normal. All right, the normal Higgs are these. And CERN agrees with. Nobody's disagreeing with anything I'm saying. They just won't talk to me about it. because I'm not peer reviewed. So we're going to peer review ourselves, and then we're going to. I want to get a guy, and I think I got a guy that he thinks he could shoot me down, or he might think he's. Well, let me put it this way: he seems like a hell of a nice guy, and wants to interact, and I think he's thinking he can knock me out of my chair, and I don't think he can. So I want him to get his guys, as many as he can get. I want anybody that wants to come against me, try going through this guy maybe. I'm going to see if I can set it up with Zoom meetings with him and me, and I'm going to make my claims, and he's going to say, well, wait a minute, how about this, how about that? And I'm going to address every issue. And if anybody has any questions or has anything like that, I want them to kick in, because I signed up for a Zoom, professional type Zoom thing where I can get people that respond, and I can have a whole bunch of different people. And somebody, this guy might host these meetings. That's what I'm hoping for, because he's very well accomplished in every realm that I can see from a brief discussion with him. But he's obviously from the mainstream. So this is what I want, is somebody that has the ability like this. And I have a couple other guys that are also, some of them are totally against me, some of them are with me. That's how it's going to go. And if I present the evidence, I would assume somebody would have to acquiesce. They'd say, wait, geez, I don't know, maybe this does make sense. But that's what I want. I want somebody who has an open mind. I don't want to just be insulted, which is my previous history. So anyway, you just saw what happened. We have the Higgs, we have the oddball particle, we have the black and whites, we have exciting the fields in the air, we have light slowing down, speeding up. Let me show you one or two last things about light actually interacting with light. Okay, this is pulsed red laser. And all the things I've shown you basically stemmed from this light. And it would normally just go like that, and you wouldn't even see it get really, really glowy, but it'd get pretty glowy at the tip. This is the leading tip just as it got turned on. What's out here? Why all these little glowy bits everywhere? These are particles that are in the air, which are gases and heat molecules. All right. Those little molecules have extra little electrons attached to them, which glow. Water molecules will glow, H2O, all of that stuff. All of the gases in the air also have electrons. They're all made from these same particles. So this is the pusher, which is the field. There's a big field surrounding a little tiny particle. We'll see in a second, because it'll start to pull that particle out as it accelerates. So don't forget, here's our field, which is creating a big disturbance in the atmosphere in front, making all of that stuff glow. So that gives us a particle wave duality, and it's strictly because there's a magnetism surrounding this. All right, it's like a balloon surrounding a particle in the center of a balloon. So you have a particle in the center, and you have the balloon part is the wave, which is nothing more than a magnetic field. It encases that particle. Now, remember, I've been arguing for dipoles since the first time I went to college, and I had real issues there, saying that it had to be a dipole. Now, again, we are using photons. You see, remember when the Yale teacher there was talking about nobody understood the quantum mechanics, and nobody does. And then he talked about Feynman. Well, this is a Feynman diagram. What are we seeing here? This is coming up here and coming back down here, bouncing up and bouncing down. This one's coming down here and bouncing up. What are these? These are protons. Okay, they're protons. These are gigantic. These are like these particles right here. You see that? A bazillion little ones. Now, one's coming here, one's coming here. If they get too close to each other, the Casimir effect kicks in, which is field push to shove. That's what I call it now. That's the new terminology, is push to shove. One of them normally, he's showing them nice and evenly. Normally one comes in real hard against the other one. They're not exactly in the same like this. So the push to shove, usually one of them I call the hard pusher is the push. The shove backer is the guy that shoves back. But regardless of who's pushing and who's shoving, you are going to emit the W and Z boson, which is the white and the black particle, which I showed you very clearly. Now, because they're using protons, they think this just came from nowhere. That just is a ghost particle, they call them. It's just, well, it just appears from nowhere land. No, it doesn't. It's one of the electrons that was in here that is no longer an electron. It's now a white and a black particle, which is the electron split in half. Simple as that. Feynman diagrams, I can explain them all day long. That's the black particle, that's the white particle. All right? They're using protons. We use photons. The photons just split. Let's take a quick look. Okay, my friends, let's talk about electrons. How can we create electrons? Well, a Tesla coil. You ever see a Tesla coil sit there, all these things are going? There's nothing more than electrons. Static that you collect on you is free electrons, and they are electrons. When you touch a water pipe or something, snap, you get that snap. Lightning, free electrons. It's excess electrons. Now, he's got a Tesla coil in his hand there. That's a tiny little Tesla coil. He can actually touch that and make it go bzzz to his finger. It hurts, but it won't kill you. It's just extremely high, pushing small amounts of electrons. Now, he's got a gas in here and a fluorescent thing or something in here, which you can see the electron beam flow from one side to the other. Now, here he goes. He's going to run it, and listen to what I has to say. Really good teacher.
All right. Now, this is...
You see, when he puts that right next to there, that's actually, it's shooting the electricity. He takes it away, it'll stop.
kind of interesting. Watch.
Now, don't forget, he's got the beam going straight across. This is called a Crookes tube.
This?
He's got a magnet. See that? He's pulling the electrons towards the magnet. So he's got a positive coming, which is the dipole, towards the negative to pull it up. Now, let's continue on. So he's pulling it up, pulling it up, pulling it up, pulling it up. If he goes down, and he only does for one step, yeah, I missed it, but he goes down. You can go down and pull it down. You can pull it up. Doesn't matter. It's just the polarity of that magnetic. Oh, here it's going down just a smidge and coming back up. It wants to get to this pole. Let's see. This could be a good spot. All right. So here he is.
Following the magnet, reacting to the magnet, deflecting the magnet.
See, now it was going down.
Okay. So.
All right. That's enough. He's stopping. It was he did a real good job. And this is LHS Atkins, Crookes tube and electrons. That's what we just saw. Now, that's enough for that one. Now, what do we have here? Arbor science, radiometer, see the energy of light. This is very, very cool. Now, let me turn this down because it was quite loud. Here goes. This is Arbor Scientific. This is a radiometer.
Most people are familiar with the light mill radiometer. You shine light on it, and it spins. The tiny air pressure inside changes to a bit higher on the dark side, which pushes it into motion. This happens because the black side heats up faster than the white side.
You see that? When they shine light on it, the black side is absorbing the particles of light. Now, I can't account for that 100%. I know it is absorbing them. So when you have black, it's not reflective. Not reflective means there's no bounce to it specifically, and the bounce is the white particles. So now it's got bounce. So now it will push away from incoming white particles, and that's exactly what happens, because the black side is the one that takes off. Watch.
The radiometer is mostly evacuated, which I will prove here by cracking this one open underwater.
All right, what does that mean? A vacuum means that there was nothing for it to bump into inside here, no other air molecules, which are big, heavy things compared to light. When you shine light, it goes right through there, no problem whatsoever. Other gas molecules don't invade this glass, much, much bigger. So the light easily goes through. And heat is nothing more than light, but it's like half of light. And I can show this in this very well too. This is a really good video. Now, so he is showing that there's almost no air in this whatsoever. And if there was air in there, it wouldn't spin. It would just be too much resistance to it spinning. So now, here it goes.
It is not a full vacuum, however. But what most people don't emphasize is that the radiometer is driven not by light, but by heat. And you can illustrate this by pouring some hot water on top.
You see the hot water
It
make it
begins
push?
to spin very quickly.
Now watch this.
Now, watch this.
This is cool.
Cold water. Wait. Now it's spinning backwards.
This blew my mind when I saw this. Wasn't that cool? Okay, my friends, I just got off a little quick meeting with Jim Boland, I'm going to be doing interactive videos with him because he's fully aware of mainstream science, and I have a whole bunch of other people that are too. And he's really going to be confronting me with the mainstream, which I don't think he's going to have any support unless he can find somebody that can stand behind him. And I can't find any other scientists that'll stand up because they can't confront the evidence. So I'm hoping he'll find somebody. He's starting a Facebook page to put this stuff out into the mainstream because, you know, we need to get it shown. And the next ones are going to be about the interaction of the Earth with the particles that are in space, which are nothing more than the particles of light, which I think I just showed you, are particles. And they have a positive and a negative charge to them, which means our ionosphere is scrubbing against them, which means it's extremely hot. So that's another thing we're going to be talking about. All right, I love you all. Stick with me. Like I say, this is not a quickie. This is going to last for a long time because we have to be able to confront every single thing that's been not understood in the physics realm, which is dark matter, dark energy, gravity, if you can believe it or not. Everything really now they realize the proton is not just one big charge. Obviously, because they can break it apart. And they break it apart and they find the particles that I showed you. So we're going to continue on until this is understood and we can get some real physics and hopefully even get some free energy. If that happens, it's golden, man. And if not, it's not golden. Not golden at all. Okay, I'm going to leave it at this for today. I think I mentioned to you Jim Boland is going to be doing Zoom meetings with me. He's fully aware of mainstream, no question, and he had very important position with our Army Corps of Engineers. Now listen to this. Welcome to Geology World. I've been allowed to join their group. Let's see what happens. However, Archaeology and Civilization, your comment was removed by the admins. Your comment was removed from Geology World by the admins. You temporarily can't post any comments in a secret of vibration. All I was doing was asking questions. This is what I'm up against. So Jim, I believe, has agreed to start a group that will highlight my evidence against these kind of people. And we're going to, you know, I'm going to be posting up there what I claim to be supportable evidence, and then let's see who will stand up from the geology world instead of just telling me to go away. I don't think this is right. Here, listen to this. This is Ancient Secret Discoveries. They're talking about the Kali Yuga, and that's the existence of human beings over 2 billion years. Now, it's very interesting, but this I found extremely interesting. Listen.
And Darwin were not exactly on the same page once all of the dust settled. Wallace had a different...
Wait, before she goes on, Darwin theory of evolution, he worked on it for 20 years. And it was well known what he was working on, but he didn't publish it. So now listen to this.
viewpoint than Darwin.
Yes, well, it's interesting what happened. They had a very interesting relationship. You know, Darwin had gone on this expedition where he sailed around the world to the Galapagos Islands and places like that. And that's where he first got this idea of evolution. So he went back to England and he began writing a book, but it took him about 20 years. After 20 years, he still had not published his theory. And he was sitting in England, and one day he got a letter from Wallace, another scientist, a younger scientist, in which he found a paper outlining the theory of evolution by natural selection. And Wallace said he was going to present it at a meeting of a scientific society in England and get it published.
All right, I just want to make a statement. I have been trying to get my information published for 6 or 7 years. Now, if you can present it and get it published, and then they can shoot it down, that's fine. This is exactly what's going to happen to me. Somebody's going to take credit for my research because they won't publish me because I'm not a member of the club. Now, in this case, they were both the members of the club, but this guy just jumped in front of Darwin, so he took the credit for it. Listen.
And Darwin, at that time, was just shocked. You know, he'd been working on this theory of evolution for 20 years, and the way it works in the scientific world is that the first person who publishes the theory gets their name on it. So Darwin called all of his scientific friends together and told them what had happened. And they said, well, there's only one thing you could really do, is you could ask Wallace if, along with his paper, a paper by you, Darwin, could also be presented at the same meeting of this scientific society. It's called the Linnean Society in England.
All right, I don't have to go any further. Now we have the internet. You can broadcast stuff out everywhere. But as I think I probably showed you, I am blocked everywhere. They just keep blocking me. Everywhere I post, they take my comments down because I am not part of the club. And my comments inevitably go against what we're being told because what we're being told isn't right. And it's not only not right in geology and history, physics, light, everything, energy, all of that stuff is wrong. So they treat me like a really bad guy. And all I'm trying to do is bring evidence to say, let's look at this stuff. And they won't do it. And this is what, my point is that I see them all now starting to change and say, oh, look what we found, look what we found, look what we found. Oh, guess what? Now light can exceed the speed of light. And oh, guess what? Now we're finding tetraquarks. And oh, guess what? This. It's all my stuff. So if you're not part of the herd there, you're cut out. So that's why I'm starting a school. Anyway, it's just a fact of nature. But this was very interesting. This is Kali Yuga, evidence of the existence of human species over 2 billion years ago. And as far as I can determine now, I see no reason to discount anything. I look at everything now. But I have to admit, the thing that strikes me most in a religious realm is that there was a guy named Jesus Christ that said he was the son of the top God, and I can't see any reason to discount that from what they say he was able to do and things. and even he said we're in a real bad time now. A lot of war and devastation, and you go through these phases: the golden age, the silver age, the bronze age, the iron age, and now we're into the silicon age, which is Star Wars.